Hello, in this video we'll discuss section 8.5, critical points and optimization. We'd like to be able to find extreme values for a function of two variables, and as we'll see, the techniques and calculus involved are very similar to what we used for a function of a single variable. So, a function has a local extreme value, either a local min or a local max, at a point where it takes on the largest or smallest value in a small region around the point. Global extrema are the largest or smallest value anywhere. Let's take a look at this surface. Right away you see there are three peaks and at least one valley. These three peaks would be local maximum values. And the tallest peak, which is shown in red here, would be the global maximum value. This valley shown in blue would be a local minimum, and it appears there's another valley behind this peak on the left, so it's hard to say right at the moment which of these local minimum values would be the global min. So just like with a function of a single variable, we're going to determine critical points, and these will be the candidates for where a local maximum or minimum value can occur. So let's define a critical point. An interior point of the domain of a function, f of x, y, where both the partial derivative with respect to x and the partial derivative with respect to y are 0, or where one or both of these partial derivatives do not exist, is a critical point of f. So we should note that we need the partial derivatives to be 0 simultaneously. As I mentioned, the critical points are the candidates for where a minimum or maximum value will occur. We have the second derivative test for functions of two variables to help us decide if we do have a max or a min. Suppose x naught, y naught is a critical point where the partial derivative with respect to x, evaluated at the point x naught, y naught, is 0, and the partial derivative with respect to y, evaluated at x naught, y naught, is equal to 0. So the partial derivatives are simultaneously 0 at our critical point. We compute this thing called a discriminant, which we'll denote by d. It's equal to the second order partial derivative, f sub xx, times the second order partial derivative, f sub yy, minus the mixed partial derivative, f sub xy squared. If the discriminant d is positive, then the function f will either have a local minimum or a local maximum, and it depends on the sign of the second order partial derivative, f sub xx. If f sub xx is positive, then f has a local minimum at our critical point, and if f sub xx is negative, then f has a local maximum at our critical point. If d, the discriminant, is negative, then f has what's called a saddle point at our critical point. Here's a graph with a saddle point at the red dot. So notice if we move in the x direction away from this saddle point, the function is decreasing. The function values are getting smaller. If we move in the y direction away from this saddle point, the function is increasing. The function values are getting bigger. So that's what we mean by a saddle point. The other option is that the discriminant d is 0, in which case the test is inconclusive and should not be used. Here's an example. Let f of xy equal x cubed plus y squared minus 3x squared plus 10y plus 6. Find all the critical points and determine whether each is a local maximum, local minimum, a saddle point, or none of these. Let me first display the graph of the surface. It looks something like this. Notice I've got 2 points labeled in yellow. We'll see why in a bit. So we need to start by finding the first order partial derivatives. The partial derivative with respect to x would be 3x squared minus 6x. Remember here we're treating y as a constant. So for example, the derivative of this y squared term would be 0. The derivative of the 10y term would be 0. And of course the derivative of 6 is 0. And then because the remaining terms only involve x's, we just take the derivative like normal. For the partial derivative with respect to y, we'd have 2y plus 10. Here I'm treating x as a constant, so this x cubed term would have derivative 0. The minus 3x squared term would have derivative 0, and the derivative of 6 is 0. Now you take the derivative of the remaining terms, which only involve y's, just like normal. So once you have the first order partial derivatives, you'll set each of those equal to 0. I should point out that these are defined for all x and all y respectively. So a critical point will only arise from the first order partial derivatives being simultaneously 0. That's why I want to set each of these equal to 0. If you set f sub x equal to 0, you see that x equals 0 or x equals 2. And if you set f sub y equal to 0, you see that y equals negative 5. So now to determine the critical points, we just want to form all possible ordered pairs involving these x and y values. So I'll pair x equals 0 with y equals negative 5, and I'll pair x equals 2 with y equals negative 5 to get these two critical points. The next step is to compute the discriminant d, and for that we'll need the second order partial derivative f sub x. So now I go back to f sub x and take the partial derivative with respect to x. Well, here's f sub x. There are no y's, so we just take the derivative like normal to get 6x minus 6. For f sub y, we need the partial derivative with respect to y of f sub y. There are no x's here, so we'll take the derivative like normal to get 2. And finally, you'll need the mixed partial derivative f sub xy, which is the partial derivative with respect to y of f sub x. Notice there are no y's here. We're treating x as a constant, and so its derivative is 0. Now we have everything we need to determine the discriminant d. It's equal to f sub xx times f sub yy minus f sub xy squared. That gives us 6x minus 6 times 2 minus 0 squared, or 12x minus 12. So now we can use the second derivative test. Let's focus on the first critical point, 0, negative 5. The discriminant is equal to 12x minus 12, but now I'm going to sub in x equals 0 to get 12 times 0 minus 12, or negative 12, which is negative. So by the second derivative test, f has a saddle point at this critical point, 0, negative 5. Working with the other critical point, 2, negative 5, we see that the discriminant is equal to 12 times 2 minus 12, or 12, which is positive. So to decide if we have a local min or a local max at this critical point, we need to also check the value of f sub xx. And this happens to be 6 times 2 minus 6, or 6, which is positive. So by the second derivative test, f has a local minimum at the point 2, -5. And that's what we see here. That's why I labeled these 2 points in yellow. The point 2, -5 is a local min. It's kind of the valley here. And the point 0, -5 is a saddle point. As you move in the x direction, the function is decreasing away from this point. And as you move in the y direction, the function is increasing away from this point. So that wraps up our discussion of the second derivative test. I'll see you next time.